If conservation is the effort to save or conserve our resources from being used up, efficiency is the practice of getting as much out of each resource as possible, of exploiting these resources as efficiently as possible. So please understand these concepts, in particular a megawatt versus negawatts, where you might generate megawatts or build a megawatt facility in order to provide more energy, as opposed to enacting conservation methods or efficiency whereby you don't need to use as much energy. Energy saved is the same as energy generated. And so let's differentiate efficiency versus conservation. You might insulate your house and it would be more efficient in its use of heat, or you dress up and stay in the cold. You could drive a Prius, which uses gasoline more efficiently, or you could drive less often, ride a bike, or walk. This is a technology exchange whereby your behavior doesn't change. This is a behavior change explicitly to conserve our resources. Amory Levins, in 1976, made a seminal paper called The Road Not Taken, where he looked at the path that we're on, the hard energy path of fossil fuels and increasing energy use. We would refer to this as business as usual. We can see gas and oil, we run out of them, and they're replaced with coal and nuclear to satisfy our ever-growing need for energy. He offers an alternative of the soft path, whereby our energy needs are greatly reduced due to increased efficiency measures, and we phase out both coal and gas, fossil fuels, in favor of soft technologies such as wind and solar power. We're right here now, and potentially we're doing both. Let's take a look. Our energy intensity is how much energy it takes us to make $1. We like when this drops. It means we're using our energy more efficiently. We can see it's always been dropping as our technology improves. But what happened here? Oh, in the 70s, with Art Rosenfeld and increased efficiency and an increased attention on energy after the OPEC oil embargo. How about here? Ronald Reagan's elected president and efficiency is not as important as getting more energy. And our energy intensity continues to drop today because of computerization. We can see even now we're not close to France. This graph shows how electricity use per person has grown throughout the years as the United States has become more affluent. However, although California also became more affluent during this period of time, its electricity use stopped increasing in the 70s with increased efficiency measures. To put things in scale, this line represents the average power consumption per person of 1,000 watts. California is a little bit below, and the rest of the United States is a little bit above and increasing. We see that the difference in energy use between the United States and California represents more than $165 per person per year to pay for that electricity. Here we see that the red states increase at a greater rate than the blue states. The significance of this is what we call the decoupling. What we studied before is this illusion that happiness is proportional to wealth, is proportional to energy use, is proportional to carbon dioxide emissions. And what California has shown right here is that we can continue to generate greater wealth without increasing our energy use. We've decoupled this relationship right here. So what measures can we take to reduce our electricity use over time? The government can support the development of efficient technologies for both the consumer and producers, but it can also pass policies that will help to change public behavior in a direction that uses less energy. This graph shows the amount of electricity saved every year as a function of the year with respect to business as usual. The government was able to achieve these results through two different mechanisms. We can distinguish command and control mechanisms from market mechanisms. We see them represented separately here on the graph. By command and control mechanism, the government can ban the use of certain technologies, such as incandescent light bulbs, or requiring building codes. The government can pass standards that an appliance cannot be sold unless it consumes less than a determined amount of energy. Or the government can pass building standards that require a certain amount of insulation or certain kinds of windows. The government can also require financial incentives which simply encourage desired behavior. such as a 20 for 20% in the summer of 2005, where if you could reduce your electricity consumption by 20%, your bill was lowered an additional 20%. Together, all these policies reduced California energy use 15% from business as usual. The command and control mechanisms cost no money, and the utility efficiency programs only cost about 1% of an electrical bill. Let's see if we can calculate this ourselves. We're very familiar with the California load curve, and we can estimate the average rate of electrical consumption is about 30 gigawatts. So times the amount of time in a year, we get 280,000 gigawatt hours per year. And we divide our 40 gigawatt hours of saved electricity by that, and it's about 13%. So we've reduced our electricity consumption about 13% of its normal amount. Or we could take a look at these 40,000 gigawatts and recognize that over the course of a year, this is equivalent to 2.5 Diablo nuclear electrical power facilities. This graph represents the amount of investment each investor-owned utility, such as PG&E, was required to spend on energy efficiency programs, such as the 20% for 20%. So we can calculate the cost of conserved energy. About $500 million was spent to reduce electrical consumption with these incentive programs, 20,000 gigawatt hours per year. This corresponds to about 2.25 cents per kilowatt hour of saved electricity. So we can see that this was a very good investment because 2.25 cents is much less than the 15 cents per kilowatt hour that people have to spend on electricity, or even the about 7-8 cents per kilowatt hour it costs to generate electricity. People are highly motivated by pride, prestige, and how they are seen by others. So one effort that cost very little money was simply comparing people openly to their neighbors, where you can see the consumer's electrical consumption is compared to neighbors and the efficient neighbors as a means to incentivize them through competition. And originally, when they performed well, there was a happy face, and when they performed comparatively poorly, there was a frowny face. This proved to be so effective that they had to stop it because people called very angry that they received a frowny face. Here we can compare the cost of conserved energy through the investment in high-efficiency technologies to the cost of electricity. And again, in California, this cost is higher, about 15 cents a kilowatt hour. For all of these technologies, an investment in efficiency is much less than paying for the extra electricity. A very famous example is the refrigerator. On the y-axis, we have the average energy used per year for a unit sold in that year. The x-axis is the year. The red graph is the size of refrigerators, which grew monotonically over time. The blue data represents the energy use of these refrigerators. We can see in around 1975, new standards were imposed that required refrigerators to be more efficient, and the energy use dropped by a factor of 4, while the size of the refrigerator remained constant. It's interesting to note how refrigerator standards were developed. Essentially, you told the companies you cannot sell a refrigerator unless it uses less than this much energy. We can compare the strategies of different countries. So what we look at here is the annual energy use of a refrigerator as a function of the adjusted volume. And all the data points are all the different refrigerators you can buy. Yes, we see that the larger refrigerators require more energy use. So what the European Union did is they first threw out all the really inefficient ones, said forget them, and then they averaged the rest and said every refrigerator sold had to be more efficient than that standard. Japan did something better. They said, let's just take the real efficient refrigerators and average them. The United States coupled their standards with research at Lawrence Berkeley National Laboratory in Berkeley. They took apart every refrigerator and found the relative efficiency of each component, and using the highest efficiency component, calculated what the efficiency of that refrigerator would be. And they said every refrigerator had to be better than that in the subsequent year. Furthermore, they published a document describing exactly how they arrived at this so that the technologies were known to all manufacturers. And you can see, in 1993, every unit matched or beat the newest efficiency. And then they did it again in 2001 and set a new standard. It's interesting to note, with increased efficiency, they kept the size the same, and the price of every new refrigerator got cheaper and cheaper. This graph shows the relative energy use over the years of gas furnaces, central air conditioning, and refrigerators. The efficiency for refrigeration is measured in seasonal energy efficiency ratio because a refrigerator will have different efficiencies or different coefficient of performances in different temperatures. An air conditioner in a very hot environment is less efficient, has a lower coefficient of performance because it has to pump the heat across a greater temperature difference. So we have this here, which is a temperature adjusted coefficient of performance. In any case, we see that gas furnaces haven't gotten that much more efficient because they already were very efficient, where the central air conditioners got much better, and refrigerators got better by a factor of 4 because they utilized the improved air conditioning technology and improved insulation technologies for refrigerators. Here we see the annual electricity use just for central air conditioning in new homes of these different years. This graph represents what if you didn't make any improvements to insulation or refrigeration technologies. The pink graph shows energy use considering the improved air conditioning technologies, and the yellow graph shows energy use considering both the improved air conditioning technologies and improved building codes with greater insulation that comply with Title 24 requirements. So we can see with respect to business as usual, our technologies have resulted in homes that are refrigerated with 1/4 the amount of electricity. We want our windows to be transparent to visible light, but yet insulate our buildings so we don't get hot in the day and we don't get cold at night. We consider the 3 kinds of heat flow: convective heat flow, conductive heat flow, and radiative heat flow, and we look at how can we stop all 3 of them. The first is with multiple panes of glass. Double wall glass and even triple wall glass is very effective at stopping the convective heat flow. San Luis Obispo is a relatively mild environment, so triple wall glass is non-existent. The only place I've seen it is in the windows of the refrigerator of Sally Lou's Cafe, so check it out sometime. We can reduce conduction by making the 2 panes of glass reasonably far apart, but if they're too far apart, it will encourage convection. It turns out that the ideal distance is about 1/2 inch. We can reduce radiative heat flow by using low emissivity coatings. We want the glass to be transparent to visible light so we can see through it, but can be opaque or reflect infrared light, preventing the infrared portion of the solar spectrum from warming up our houses in the day and preventing our homes from cooling off because at room temperatures we radiate almost only infrared. And so you can see this is the transmission spectrum of the new coatings on the glass. Here's visible light. The glass is largely transparent to visible light, but in the infrared out here, it is almost all reflected. We can control the transparency of our glass, which can be very useful, such as in these glasses, by using liquid crystal window technologies, which take a liquid crystal and can orient the molecules to be opaque or transparent using an electric field. And this is all being studied at Lawrence Berkeley National Laboratory in Berkeley, California, at a dedicated research facility.